having me here. For the past week and a half, we have heard a lot about how to model binary systems in the context of general relativity. But of course, one important question, scientific question that one may want to address with the observation of gravitational waves is whether GR is the correct theory that at this scale, and whether we can place interesting constraints on alternative theories of gravity. So this is the general context of this talk. So specifically, I'm going to tell you a little bit about this work done in collaboration with Mohammed Khalid, Nestor Ortiz, and Jan Steinhoff, which deals with an effective action model for this effect that's called dynamical scalarization. This is an interesting effect that happens in a class of modified theories of gravity. But I'd like to slowly build up to that. So I'm going to start with a very general introduction and discussing the broader aim of this type of research. And then I'll discuss how to set up the typical post-Newtonian expansion in this modified theories of gravity. Then I'll discuss how the typical post-Newtonian expansion fails to capture some interesting non-perturbative effects that may happen in this series. And then I'll discuss a couple of proposals to accommodate this effect in a perturbative treatment. So here I'll define what I mean by the scalarization, spontaneous and dynamical scalarization. Then I'll discuss in a little bit more detail the effective action model that we have worked on and the specific improvements that we did in that action. Okay, so before showing some actions for modified theories of gravity, I think it's always interesting just to start by revisiting the experimental basis of general relativity, which is, after all, what makes it so successful. So really, at the bottom, we can think of experiments that prove the basic principles on which not only general relativity, but a wide class of modified alternatives to GR are based. So these are principles like the weak equivalence principle, the universality of free fall, local Lorentz invariance, and local position invariance. Together, these are sometimes referred to as the Einstein equivalence principle. And testing this motivates experiments old and new. So just to give one example of a recent experiment that is designed to test the weak equivalence principle is the microscope mission, which is sensitive to deviations of 1 part in 10 to 15. And of course, the Einstein equivalence principle is at the basis not only of GR, but of all metric theories of gravity. And by that, I mean theories not only which are endowed with a metric field, but in which free particles, test particles, follow geodesics of that metric. And in the freely falling frames associated with that motion, we recover the laws of special relativity. So given that the weak equivalence principle in particular is so well tested, we can maybe restrict to metric theories of gravity and then consider tests of their equations of the field equations. So that can be done in several contexts. First, we can think perhaps of testing the theories in our neighborhood in the solar system. So here, gravity is weak, velocities are non-relativistic, and just the first post-Newtonian corrections to Newtonian gravity are relevant here. So here in this context, there exists an interesting framework, which is called the parametrized post-Newtonian or PPN framework, that completely parametrizes or parameterizes in a theory-independent way all possible deviations from GR, assuming some small hypothesis. And this is basically based on writing down the most general metrics, the first post-Newtonian order, and placing in front of all possible potentials some phenomenological parameters, which are meant to be contrasted with observations. So the classical tests of general relativity put constraints of those parameters, and this also motivates like modern incarnations like the BP-Colombo mission, which is set to improve the precision to which the per-Higgins defense of Mercury is measured in about 1 million times. So this was launched in 2018. And then we can move to maybe our main interest here, which is tests of the theory of gravity in the strong gravity regime. And this is par excellence the regime, the vicinity of black holes and neutron stars. And in this regime, we can also like distinguish maybe two situations one which is quasi-stationary, which is characteristic, for instance, of pulsars in binary systems, and the other which is highly dynamical, which is characteristic of the coalescence and merger of binary systems. And we can also think about tests of theory of gravity in the radiative regime, where the gravitational field itself is weak, but we want to test properties of gravitational waves like polarizations and things like that. Okay, so when we think about modeling binary systems, a major tool is provided by the Poisson-Thornen expansion. So the Poisson-Thornen expansion essentially expands the field equations in some small parameters. So here we consider the ratio between the orbital velocity and the speed of light, the square of which scales like the interbody potential, the mass divided by the orbital distance. But in the typical Poisson-Thornen expansion, one also expands on internal parameters like the internal velocities of the stars and the compactness of the stars. So strictly speaking, the Poisson-Thornen expansion is adequate for slowly moving and weakly gravitating objects. However, even if the individual bodies are black holes or neutron stars, which mean that they are strongly gravitating, some sort of Poisson-Thornen expansion for the orbital motion still works. And this is especially true in general relativity because GR obeys not only the weak equivalence principle, but also what we call the strong equivalence principle, which is essentially the extension of the universality of free fall to self-gravitating bodies. However, when we go to modify theories of gravity, one often finds the situation where the strong equivalence principle is not satisfied. So, I mean, the strong equivalence principle in GR is related to the fact that, effects that depend on the internal structure of the bodies, they exist, but they are extremely subdominant. So indeed, apart from tidal interactions that depend upon the finite extent of the bodies, the orbital motion is essentially governed by masses and angular momentum, which are quantities that are global and do not depend on internal properties. But when we go to modify theories of gravity, they in general are not going to obey the strong equivalence principle. And then we can see that this internal defects that depending on the internal structure, they appear much earlier than in GR. And in sometimes they may appear in non-perturbative ways. So this is what I'd like to talk about. But for that, I'm going just to restrict our discussion from the rest of the talk to the simplest possible theories where the kind of effect that I'll discuss here appear. So you can check, for instance, in this paper, a bunch of different theories that exhibit more or less a similar phenomenology. Here I'm going just to stay in the simplest class. So what we have here, so Psi-m here denotes our matter fields. And in the series, this matter fields couple universally to a single second rank symmetric tensor, which we sometimes call the Jordan frame or the physical metric, which is decorated here with a tilde. So it satisfies the weak equivalence principle. However, the difference between these theories and GR is that this physical metric is not a pure spin-2 field, but instead is a mixing of spin-2 and spin-0 contributions. So here, G without a tilde is what we sometimes call the Einstein frame metric, for which the relevant term in the action is just the Einstein-Hilbert term. And for the scalar field, I'm just including here a kinetic term. You can put self-interactions, more scalar fields, to whatever you want. So this is the simplest scenario that exhibits the basic phenomenology that I'm going to discuss. Okay, so from a fundamental point of view, this matter action should be constructed by building the curved spacetime version of the action of whatever fields are present in your description, with the non-minimal coupling procedure referring to G tilde, to the physical metric. However, we know that phenomenologically, sometimes it's a good approximation to treat the motion of binary and body systems as phenomenologically as one part. So here we have just the action as in GR, but everything refers to the Jordan frame. So now you can see, okay, so and this Jordan frame masses, they are constant as in GR. So now one can plug into the line element this conformal transformation and write the line element in terms of Einstein frame quantities. And maybe it's natural to define this, field-dependent quantity here as the Einstein frame mass, right? So this Einstein frame mass carries some field dependence, but this field dependence is universal. Okay, so this action is interesting for us if we have non-self-gravitating point particles. And this can be a good starting point in general relativity, even if we have strongly self-gravitating bodies like neutron stars, because GR obeys the strong equivalence principle, at least, I mean, if we ignore rotation. However, when we go to modify theories of gravity, and this in particular, we find that the stellar properties, they depend on the scalar field environment. In particular, the star's gravitational binding energy, which contributes to a fraction of the star's mass, is field dependent. So a way to introduce this phenomenologically in this model, and which has proven very successful, was pioneered by early in the 70s. And the idea here is to promote these masses to field-dependent quantities and object-dependent quantities. So the field dependence may be object-depending in such a way that not only the Einstein frame mass, but the Jordan frame mass depend on the scalar field. Okay, so this is our starting point for instance, the post-Newtonian treatment. And here I'm just going to sketch the idea following this work by Damour and Fahez. So there are several ways to do the post-Newtonian expansion in scalar tensor theories, like the method of direct integration of relaxed Einstein equations, which has been extended successfully to this context. But here they follow a more field theoretical approach, which I thought it would be more natural for this audience, although I'm not a super expert in QFT techniques. So the idea here is basically the following. So let us denote by capital Phi our field variables, so the difference between the Einstein frame metric and the flat metric, and also the difference between the scalar field and its asymptotic value, which I'm calling here this phi. And let us also denote by sigma the matter variable. So the total action can be written as the sum of a field-dependent part on which we already include some gauge fixing terms in order for the kinetic term to be invertible, and a matter part which depends on the matter variables of the field.
So what is F nu comma?
It's just F minus, just eta, just what they use for the flat metric Minkowski.
Okay, and the comma is derivative with respect.
No, it's not the derivative. It's just that we are going to so we are going to denote by phi both these variables and that variable. So it's just the perturbation of the metric and the scalar field. We're going to denote collectively by the perturbations in the fields. So these are just a notation for both fields.
Phi zero, it's so we are effective not of this scalar tensor because scalar, and phi zero would be the action of matter.
Phi zero here plays the same role as the flat metric. So this is the boundary condition at spatial infinity. So I mean, physically, this is set by some cosmological evolution, which we are neglect. But from this perspective, it's just a constant. Okay, so from the total action, varying this with respect to the fields, we get the field equations. Varying with respect to the matter variables, we get the equations of motion. And then the strategy here in this work is basically the following. So it's basically to solve the field equations perturbatively to a given order in G. So this is a nonlinearity extension. And let phi bar denotes this perturbative solution. One then construct an effective Fokker action by simply plugging in the total action the solution that we had before. So like this, they construct the two, like an n-body actually Lagrangian up to second post-Newtonian order in this So just to say the same thing in the diagrammatic language, so here let a straight line denote the propagator, white blob the matter variables, black dot essentially the D'Alembert of the fields. And so the steps that I mentioned before are essentially the following. So first, one solves the field equations perturbatively, which in this diagrammatic language essentially means replacing the field by some combination of the matter variables. Then the second step is to first expand the total action up to the desired order in G, and then applying those rules iteratively in order to get your action, your expanded action, Fokker action. And the final step is just to take into account that, well, here we have a notation that accounts both for scalar interactions and gravitational interactions, and then we need to account for that. And up to this point, the expansion is just a nonlinearity, it's just an expansion in G, and then in the end, one can also expand in the velocities and the compactness. I'm going to tell where the compactness enters. Okay, so following this approach, one can recover known results in the series. For instance, in the Newtonian limit, what we have is that, what we find is essentially that the bare gravitational constant gets replaced by some effective gravitational coupling. So in a diagrammatic language, at this order, we have essentially these two diagrams, one which represents the gravitational force and also a second one that represents the scalar force. And notice that this scalar force is proportional to what I'm going to call here the scalar charges. So this alpha here is just the log derivative of those field-dependent Einstein frame masses. And this is to be evaluated at the background value of the scalar field. Right. So we can move on and then compute the first post-Newtonian corrections. They find, well, it was found previously that the first post-Newtonian corrections are essentially governed by two new coefficients, this gamma and beta, which also depend on the scalar charges and on derivatives of the scalar charges. So what they do in this paper is to push this to second post-Newtonian order and find that the second post-Newtonian order, we have two new parameters that govern all the scalar dependent effects, which are also proportional to the scalar charges and the higher derivatives of the scalar charge. So I don't want to go into the details, but instead focus on some general thing that we can learn from this analysis, which is the following. So from this type of treatment, one can show that for any post-Newtonian order, the scalar field-dependent corrections are going to be proportional to a factor of the scalar charge squared. Now, you remember that the scalar charge is just this log derivative of those field-dependent masses. And remember that the Einstein frame mass is related to the Jordan frame mass by this by the coupling function that defines the theory. And recall also that when we have non-self-gravitating bodies, the Jordan frame masses are constant. So it's natural to imagine expanding the scalar charge around the case where the bodies are non-self-gravitating. And the relevant parameter here is essentially the compactness, which is a measure of the, for instance, the gravitational binding energy. So you see that when this guy is constant, it drops from the integration. So if these guys are constant, we would have just the log derivative of A, which is this universal factor here, which I'm calling this alpha 0. And then we can imagine expanding this in powers of the stellar compactness. So following this reasoning, one would be led to conclude that since all post-Newtonian corrections are proportional to the scalar charge squared, and the scalar charge itself can be written in terms of this universal factor, essentially what we are probing here is only this factor, and this is probed, for instance, by the first post-Newtonian corrections. So to make the argument a little bit more dramatic, if we imagine a theory which has this alpha 0 equal to 0, so it can be a theory that's very different from general relativity. But if this alpha 0 is equal to 0, then this reasoning would seem to imply that this theory is indistinguishable from GR to any post-Newtonian order.
If it doesn't have self-interaction, the phi field is self-interaction, then
in the field, in the scalar field.
Yes.
Yeah, so here I'm not taking into account the potential. Yeah, but this conclusion is not true even in this context. So, and what makes, so this is what this reasoning, this argument seems to lead us, that such a theory, for instance, would be indistinguishable from GR to all post-Newtonian orders. But this is not the case. And this is essentially due to the fact that the scalar charge in some classes of modified, of scalar tensor theories is not an analytical function of the stellar compactness. So you cannot really make this expansion. So let me discuss that a little bit. But for that, let me first briefly review how this quantity is computed. So here, we have been essentially talking about this, the problem of the motion from an outer perspective, where we are essentially solving the field equation subject to some boundary conditions at infinity and in the vicinity of the world lines. However, these boundary conditions at the vicinity of the world lines should be given once we consider an inner problem, which is essentially to look at an inner world tube around each body and to consider the influence of the external bodies on the field in that inner world tube. So just to be more specific, so here imagine that R is the typical size of our, say, neutron stars, and D is the typical separation distance. And let us define some matching radius, which is much larger than R and much smaller than D, in such a way that these two ratios are equally small. So what we have been doing is essentially taking this epsilon going to zero limit and looking at this at the point of view of the outer problem. So from the point of view of the outer problem, this essentially means taking this R max to zero and collapsing the stars into point particles. However, when we think about the same limit, but from the perspective of the inner problem, this means essentially taking R match to infinity when it's measured in units of R. So the idea of the inner problem is essentially especially when we're taking this epsilon equal to zero limit, is essentially to look. So when we are looking at the inner problem at the epsilon going to zero limit, we are essentially solving for an isolated stationary star, which is subject to some boundary condition at this matching radius, which in this epsilon going to zero limit corresponds just to spatial infinity. So from the perspective of the inner problem, we essentially have to solve TOV-like equations or the equations of hydrostatic or hydrostationary equilibrium with the boundary conditions given, some boundary conditions given this matching radius. So choosing some proper coordinate system, the metric at the metric radius reduces to the flat metric, and the scalar field goes to some constant, right? So it can be shown, we can check, for instance, this SAIFR, that far away from this object, the metric has the usual Schwarzschild-like behavior. So we can read from the metric the mass of the star as a function of the boundary condition that we put in this matching radius. And also the scalar field has also one over R decay, and the scalar monopole moment here is proportional to the scalar charge. So in practice, how do we compute these things? In practice, we look at how the mass and the scalar, how the metric and scalar field behave at far away from the star when we change these boundary conditions, but solving the full equations of motion for the star itself. Okay, so this is how we compute those things. So let us get back to our previous discussion, where I was telling you that in some cases, this expansion of the scalar charge in terms of the stellar compactness is inappropriate. So this is just a specific example for a specific theory. So here I'm considering a theory which has, it's basically a scalar field with a term in direction that's proportional to R phi squared, with this psi here being a constant coupling. And although this theory is not in the form that I mentioned before, it can be cast in that form by a conformal transformation of the metric. So there is a mathematical correspondence between the two. So what we have here is that in this theories in particular, we find that alpha 0, which is the log derivative of the basic function that defines the theory, is proportional to the asymptotic value of the scalar field. And here I'm plotting the scalar charge of a neutron star with a given equation of state for a specific field coupling here, and two values of the asymptotic scalar field. So what you see here is that outside of this colored region, so for low central densities and high central densities, the behavior of the scalar charge is essentially given like that. So how do we see that? So as we decrease the scalar field, and therefore in this theory, if we decrease the asymptotic value of the scalar field, we decrease this vector of alpha 0. The scalar charge decreases accordingly, like in this equation. So we see that as it decreases the scalar field, the scalar charge decreases accordingly. But in the colored region here, so in some region for some parameters for describing the star and for some range of field couplings, this does not hold. So what we see, especially in the limit where the asymptotic value goes to 0, is that the scalar charge goes to 0 outside of this region, and then has a sharp growth inside this scalarization region. So this is essentially, so the scalar charge is continuous, but the derivative is not continuous. So this is characteristic of a second order phase transition, like spontaneous magnetization, ferromagnetism, and therefore this effect has been dubbed spontaneous scalarization. So we have a situation where we turn off the scalar interaction outside the star, but even then the star has a non-negligible scalar cloud around it and scalar charge. Okay, so you can argue, well, okay, this expansion is not appropriate. We should just not do it, right? So one can think that going back to our previous discussion, there is an easy way to accommodate spontaneous scalarization, this perturbative effect, which is to do just a partial resummation of these quantities, or just avoid from the onset expanding on those, and just keep the expansion on the orbital quantities. And this has been, this is called the post-Keplerian formalism. The name is because the parameterized post-Keplerian formalism is something that has been very successfully applied to poster timing. And well, one can do that in the setup that I described before. Like it's very natural. It's very easy to do that. Okay, and this then post-Keplerian expansion has been very successfully applied, as I said before, to the version of binary posters. So when you have a poster in a binary system, the post profile gets modulated by the orbital motion. And by studying those modulations, you can infer several properties, not only Keplerian properties of the orbital motion, but also some relativistic effects. So here I'm just illustrating for a simple case where we have a poster white dwarf binary system. In this case, in particular, the mass of the white dwarf is measurable independently by spectroscopy measurements. And one also can measure the mass ratio. So in the system, like in the famous Hausdorff system, one can also measure the time derivative of the orbital period, which is by assumption due to the emission of gravitational waves. And in principle, many other parameters relativistic parameters could be measured here. And the idea then of this mass diagrams is that all these measurements should intersect at a point. So when you have two neutron stars, typically the individual masses are not themselves measurable. So you can measure the masses by measuring these relativistic effects. And then if you have more relativistic effects, you have a test of your theory accuracy. And you see that GR passes this test beautifully, but not so some other classes of theories, in particular, one class that displays this effect that I was telling you about, that is this spontaneous scalarization effect. So I think this is nice because here we have a situation where there is this class of theories which is not distinguishable from general relativity from weak field experiments, but which like unleash their effects in the strong field environment, for instance, of neutron stars. And the binary pulsars turned out to be the main testing ground for this series. Okay, so is this the end? So actually, I'm just about to, this is not the end, I'm just about to introduce the main topic of the talk, which is this other effect, which is called dynamical scalarization. So in 2013, Enrico Barauste, Carlos Valenzuela, Marcelo Ponce, and Luis Zinner were studying the merger, coalescence and merger of neutron stars in this scalar tensor series, and they noticed something interesting. So here, some interesting things actually. So here I have like one example. First, they noticed that if you have a situation where one neutron star is initially scalarized, it means it has a large scalar charge, and the other star has a very low scalar charge, they noticed that quickly the field readjusts itself so that the two scalar charges become some comparable. So the color coding here is just the scalar field amplitude, which can be regarded as a measure of the scalar charge. So this was induced scalarization. But perhaps more interestingly, they showed that even two neutron stars, which are themselves too diffuse to scalarize when they are isolated, they can develop a non-trivial scalar charge when they come very close together. So this is shown, for instance, in this plot. So this is a measure of the scalar charge as a function of the orbital separation. And here you see that the scalar charge for the stars is very small when they are separate, and this is for an equal mass binary system. So the scalar charge is very small and the stars are widely separated, but as soon as they reach some critical separation, the scalar charge increases by a few orders of magnitude. So this is the effect that was then called dynamical scalarization. The stars are too diffuse to scalarize individually, but they can scalarize when you place them close together. Okay, so the typical post-Keplerian expansion does not capture this effect. So the post-Keplerian expansion says that if the stars are too diffuse to scalarize individually, the scalar charge should remain small during all the evolution. And the reason is that although the post-Keplerian formalism avoids expanding these field-dependent masses in terms of the stellar compactness, it still expands these field-dependent masses around the background value of the scalar field. So this is how it captures spontaneous scalarization. This is how it misses capturing this dynamical scalarization. And what happens here is that, as we had before, this function turns out not to be analytic. So these coefficients are very large and they overcome the smallness of this expansion parameter in some region of parameter space. So motivated by maybe our previous discussion on the post-Keplerian treatment, one could then imagine, well, we can do some resummation here as well, or not expand on this quantity. But it turns out that this difference between the scalar field and its asymptotic value is proportional to the interbody potential. So completely resumming that will just recover the full theory and not perturbative treatment. So people have come up with some sort of perturbative treatment that still is able to capture dynamical scalarization. In particular, in this paper by Noah Sennett and Alessandra Bonanno, they propose to do some partial resummation, so expand some quantities, not expand other quantities. There is some freedom there as to what is expanded. They call this the post-Dickian formalism because people like inventing names, right? And but I'm not going to go into the details here. The starting point is again this relaxed version of the Einstein or the scalar tensor field equations. But instead, I'm going to move on and discuss this effective action approach to dynamical scalarization, which I think is very simple, intuitive, and captures the essence of this effect. Okay, so this framework was initially proposed in this paper by Sennett, Shao, and Steinhoff, and later it was extended by Mohammed and Alessandra also to a theory agnostic framework for dynamical scalarization. So here I'm going to basically discuss a little bit the essence of the first, the main ideas of the first paper, and then just mention some ideas of the other. So the starting point here is the same as we had before. This point particle action with this few dependent masses, and the idea here will be to first reparameterize the action in terms of the scalar charges. So here I have been calling the scalar charge this log derivative of the field dependent masses. However, I'm going to slightly change the notation now and just call also scalar charge this q, which is just minus the derivative of m with respect to the scalar field. It measures essentially the same thing, and it has a nice interpretation. So this is an expression that I've shown already before. So you see that this q is actually gives the strength of the 1 over r decay of the scalar field, and therefore can be interpreted as the scalar monopole moment. And here q and phi, they offer what I'm going to call then the scalar charge or the scalar monopole. So these in the scalar field, they form, they give complementary descriptions of the motion. And since they form a pair, right, of conjugate variables, and indeed one can convert between the two. So that's the idea. So we are going to first define a new potential from our mass by means of Legendre transformation. And the idea will be then to promote this scalar charge to an independent degree of freedom, so that variation of the action with respect to this new degree of freedom is going to give rise to new equations of motion, which will capture a lot of the effects that I discussed. So the second step will be then to promote Q to an independent degree of freedom, but I'm going to postpone showing that. The third step is to consider a power series expansion of this function, this new potential m bar, in terms of this scalar field monopole. And here I'm keeping terms up to q to the 4th. So there are many cases where the full theory is invariant under a transformation that takes phi to minus phi. So it's natural to imagine that the Einstein frame masses are going to also inherit the symmetry, which is also equivalent to setting q to minus q. And a simplification that one can make is just to keep even terms in this expansion. Of course, the full symmetry exists only if it's respected not only at the action level, but also by the boundary conditions. So if in particular, for us to have the full symmetry, we need the asymptotic value of the scalar field to be 0. In particular, if the asymptotic value of the scalar field is not 0, one can still perform an expansion like this, but then replacing phi by this phi hat in this expression. And then you notice that there is a term that is proportional to q here, q phi 0. So we can accommodate this non-zero value of the background scalar field by simply weakly breaking the symmetry by adding this linear term. So you see that the meaning of the C1 coefficient is just the asymptotic value of the scalar field. The meaning of the C0 coefficient is just the mass of a star in general relativity where the scalar charge is 0. So the mass of the star with the same baryon mass, same rest mass. And so later on, I'm going to show in practice how to compute the C2 and C4 coefficients. But for now, I just wanted to show what is their effect and what's the phenomenology associated with this. Okay, so this approach essentially involves building the two-body Hamiltonian. And this is interesting because the two-body Hamiltonian is one of the basic building blocks in many models, many waveform models. However, here I'm going to explain the basic procedure. Just imagine that the orbital dynamics is described to the leading Newtonian order. So we could straightforwardly, more or less straightforwardly, generalize this to higher post-Newtonian orders by considering some generalization of the procedure that I sketched before. So solving the field equations perturbatively for the fields, and then replacing those in the equations of motion. So here I'm just going to illustrate at Newtonian order. So this is the solution for the TT component of the metric and the scalar field at Newtonian orbit, Newtonian order, and then we can just insert those expressions in our matter action, and we get this when we neglect the singular self-interactions. So here, V is just the Newtonian velocity, R is just the orbital separation, and from the Lagrangian we can construct the Hamiltonian by a singular genre transformation. Okay, so I said from the beginning that the idea was to promote the scalar charges to independent variables. When we do that and obtain the equations of motion for the scalar charge, we get this. So this is very straightforward. So the z is this redshift parameter, which essentially captures all m-dependent terms in the Hamiltonian. And here I have kept up to terms to q to the fourth in this expansion. So the idea is that the scalar charge is going to be the root of this cubic equation. But for us to have a clearer picture, let us make some more simplifying assumptions. So in particular, let us consider that we have an equal mass binary system so that the two scalar charges are the same. Let us consider that phi 0 is equal to 0 so that we don't have the linear term. And let us consider, just for simplicity, that this z is just 1, neglecting 1 over c squared contribution. So when we do that, the equation for the scalar charge becomes like this. And from this equation, we can notice a couple of interesting things. So first, a solution with where q is equal to 0 is always a solution of the sphere equations. However, the solution may not be unique, and it may not be stable. So in particular, the stability criterion is violated by the trivial solution if the C2 coefficient is less than 1 over the orbital separation. So we have some interesting situation here. So if you notice that if C2 is negative, so if C2 is negative, this condition is always satisfied for any orbital separation. So this means that the trivial solution is unstable, so q equal to 0 is unstable for any orbital separation. The q equal to 0 solution is unstable if the stars are essentially isolated. Well, I was going to mention this before, but whenever we find that whenever the q equal to 0 solution is unstable, there are other real solutions with different values or non-zero values of the scalar charge. Okay, so this is how this framework captures spontaneous scalarization. But then you see that even if the C2 coefficient is positive, scalarization, meaning the instability of this trivial solution and the existence of non-trivial solutions, stable non-trivial solutions, this can exist even if we have a small enough orbital separation. So this is essentially how this framework captures this effect of dynamical scalarization. So just to give a picture, so this is the two-body Hamiltonian as a function of the scalar charge and this effective C2 coefficient, which is just C2 minus 1 over R. So the solutions to the field equations are here denoted by these black lines. And you see that when the C2 coefficient is positive, we have just a single real solution for the scalar monopole, which is 0. But when this crosses 0, the solution becomes unstable, and these two new solutions develop, which have non-zero scalar charges. So this is how this framework captures in a single way spontaneous and dynamical scalarization. Okay, so there is another way. So I mentioned that later this framework was generalized to a theory agnostic framework for dynamical scalarization. So let me briefly discuss that. So the idea here, so I'm going to give basically a complementary or a different description of what we have been doing, right? So imagine that the scalar field is split into a part that has a short wavelength, so the UV part, and some part which has a long wavelength, which is the IR part. And these two scales are essentially separated by the object size. So when one think of averaging over box of the size of the star, what we do is to essentially collapse the stars to a point, and then dynamical processes like oscillations of the stars are to be represented by dynamical variables on those world lines. Okay, so keep this there. Let me show you or no, discuss something else, then we're going to connect these two things. So we know that when we have a star where whose initial scalar charge is 0, but where the solution is when we are in the parameter space for spontaneous scalarization, what happens is that this trivial solution is unstable under scalar field perturbations. So let me just show this plot, which shows this more concretely. So this is the result of a simulation that we've done some years ago. This just shows what happens when you place a star with negligible scalar charge in a theory which admits spontaneous scalarization, and where this star should be scalarized. So what happens so this is the central value of the scalar field as a function of time. And what happens then is that the central value of the scalar field and the scalar charge of the solution grows exponentially in this initial phase until it reaches a value high enough to trigger some back reaction from the fluid. And then the fluid and the scalar field evolve together in some complicated nonlinear way. But the beginning here, this first phase, is governed just by linear perturbation theory. Okay, and now if we imagine going outside or leaving this scalarization window, we would see that this time scale of exponential growth would be longer and longer and longer and longer until this fundamental scalar mode is no longer unstable. So the critical point, at the critical point for scalarization, we have that this fundamental scalar mode of the solution has a 0 frequency. So on one side it is unstable, on the other side it is stable. At the critical point, it has a 0 frequency. So around the critical point for scalarization, this scalar mode has a very long wavelength, and therefore it can be excited by these infrared fields. So the idea here in this setup is essentially to introduce the dynamics of this fundamental scalar-led mode as a new dynamical variable on the world line. And this should be excited by the infrared fields because these are long wavelength processes near the threshold for scalarization. Okay, so what we expect for the dynamics of the scalar mode is essentially some type of oscillator equation where all these coefficients here are to be determined somehow by the UV physics. And we see that, well, so the idea is to source these modes by the infrared fields. So how can we recover that from some action describing these neutron stars with this variable treated as the dynamical variable at the world line? So the idea is basically this. So we have this kinetic term for this scalar monopolar mode, some coupling that gives rise to this source. And then here I'm including not only the potential, but some constant coefficient, which has the meaning of the mass of the neutron star when there's no scalar field. So this is essentially the action that describes, the effective action that describes this neutron stars close to the critical point for scalarization. And then you see, if you recall, that this is essentially what we had before, except from this first term. So what we had before, when we considered building this Legendre potential from the Einstein frame masses, was essentially an action that looked like that. So this means that what we were doing, we were essentially using this approximation of adiabatic evolution, that the field outside evolves in a time scale that's too large compared to the characteristic time scale of the mode. However, as I mentioned before, close to the threshold of scalarization, the typical time scale for the mode is long also. So we expect this term to be important, to have some importance. Okay, so in this work with Mohammed Khalil, Nestor, and Yun, we improve on the previous models in several directions. So, for instance, we consider completely generic, I mean, eccentric or hyperbolic orbits. We include radiation reaction terms at the level of the equations of motion to better capture the evolution of the system. And perhaps more important from the perspective of the particular discussion that I'm making, is that we include then the scalar mode dynamics in the model. So I think I'm going I'm not going to go into much detail here. I was going to basically tell you how to compute all the coefficients that appear here, which are then governed, so which are to be determined by looking at this inner problem. So essentially, the C2 and C4 coefficients are obtained by a polynomial fit to the masses. So it's a procedure that's very similar to what I described before. We fix the baryon mass of the star, vary the asymptotic value of the scalar field, then construct this Legendre transformed potential, and just by fitting a polynomial to that, we can recover these coefficients. And the CQ dot coefficient, which is more maybe important from the perspective of this work, is computed from some previous calculations that we had done, where we studied the quasi-normal modes of neutron stars in the full theory. So the idea is to somehow connect what we had for the frequencies and decay timescales for those modes to a value of these coefficients, and this is done by matching this oscillator equation to what we expect to be the solution. Okay, so there in this paper we explore the full parameter space. I have a bunch of nice simulations. Here I'm just going to show one, just illustrates the main result, the main phenomenology, right? So here I'm showing one simulation where we have an equal mass binary system with an eccentricity of 0.3. So this plot shows the orbital separation as a function of time, and these two plots show the evolution of the scalar charge with respect to time. So here, the initial position, the initial separation, was chosen to lie outside of what I'm calling here this dynamical scalarization radius. So this is just defined as 1/C2, so it just depends on the baryon masses. And this, if you recall the previous discussion, is just a radius for which we would expect dynamical scalarization for circular orbits, right? So what we see here is the following. So initially, the separation is larger than this dynamical scalarization radius. But it's entering this dynamical scalarization radius. And each time it enters this DS region, what we see is that the scalar charge tries to increase. However, since the binary spends more time outside the dynamical scalarization region than inside the dynamical scalarization region, we see that overall the scalar charge decreases with time. At some point, what I'm marking here with orange is the mean orbital separation. At some point, the mean orbital separation crosses this dynamical scalarization region radius in what I'm calling this TDS here. And you see that from this time onwards, although the binary still goes outside of this DS region, the scalar charge starts to increase in an exponential-like fashion. And it increases until it reaches some saturation. Actually, it does not reach saturation, but instead it approaches this attractor solution, which is just given by the adiabatic solution that we had before. So all this initial phase of decrease in exponential growth is only captured in this model because now we have a way to include the dynamics of this scalar monopole mode. Okay, so this is essentially it, and so there are several ways to improve this model, like but really is the first step that already has much of the physics and capture these effects in a more or less intuitive way, right? So just to do a final recap, So the idea of this talk was basically to say that, well, for us to really explore the full potential of gravitational wave observations, in particular to test of general relativity, I think it's very insightful if we know how a few candidates, at least, what to expect from a few candidates that are not GR. So differently from the weak field or solar system regime, where we have this completely theory agnostic way to parameterize deviations from general relativity. In the strong field regime, we don't. So I think it's quite insightful to look at particular theories. And here I showed something that I find interesting, which is the onset of these non-perturbative effects in these classes of modified theories of gravity. And even if we think about doing some sort of like post-Einsteinian framework, right, for parameterizing deviations from general relativity, studying effects like this in particular theories can guide us to what better model to use phenomenologically to test for deviations. And yeah, that's essentially it.
Yesterday, Colin showed us the bound on the phasing of the spiral waveform. So do those bounds apply to any of your parameters? I mean, how do you check your setup against the spiral dynamics?
The fact here is that this effect that I discussed only happens for neutron stars. It does not happen for black holes. So you're thinking about and also this dynamical scalarization effect only happens. So if you pick a theory that's not already excluded by pulsar timing experiments, this dynamical scalarization effect is going to happen only in the last phases of the coalescence of a neutron star merger. So what Colin showed was for binary black holes, right?
No, that was
for a neutron star.
All depends.
All depends, yeah.
Yeah, but the
that was a little bit what we discussed yesterday. So it assumes the same deviations for all these events, but here we have a theory that predicts that black holes would be identical to GR, but neutron stars are not.
You can imagine that the ballpark of the bound will not change too much. I mean, the binary spiral we saw were very long, no? So you can expect, without redoing all the math, that they would lead to that kind of bound.
Yeah, so even though, like, if you think of a theory that's not already excluded by pulsar timing experiments, then this dynamical scalarization effect would happen in the final stages of the coalescence. And
no, but binary pulsar exclude, it's only about 1 p.m. Basically, 2 p.m.
No, I mean the theory is excluded, not so the binary pulsars exclude a class of theories like this. So if you pick the theories in a region of their parameter space that's not already ruled out by other types of observations, and which do not predict spontaneous scalarization. So if you think of a theory that predicts that these two stars, when isolated, would be just identical to GR, and you put them together, so imagine that W18 17 was like that. So the stars individually were not scalarized, but they scalarized in the final stages of the coalescence. So I don't know if you can just translate immediately those bounds on this case.
Okay,
so I never. Okay, go ahead.
Okay, the second point, but then we know that first we merger we have tidal effects in GR. So yes, this scalarization could somehow be disguised for tidal information.
Yes. So one of the effects of the arousal of the fields is precisely like to have a quicker merger than with respect to general relativity. Not only because now you can radiate in scalar waves, but also there are some conservative effects as well, like G Newton differs, so this is field dependent. So I guess a general problem when we try to probe modified theories with neutron stars is this degeneracy with equation of state effects. So the same sort of earlier merger happen if you have equation of state that predicts the star
But
state
just
law.
by thinking, I mean, it's
So
not.
I never saw like a specific like applying this really analyzing the data for the neutron star merger that we saw to rule out certain strip of parameter space in this series.
But the title, I mean, correct me if I'm wrong, but the title deformation for GW17 or 17 as sort of the order of magnitude is sort of being indicated by the data, right?
No, you can't actually measure the title.
No, you cannot measure, but you can see some indication that the order of magnitude is, I mean, 0 is not preferred, right?
So
Okay, let's see.
0 for both is, yeah, but it's, you really can only put an upper bound on the title.
You can.
Yeah, you can't, let me reword this. You can't, in the gravitational wave alone, tell that 170817 was not a finite black hole.
Okay, but so you have an upper bound on the title deformation.
Yeah, no,
it must have been smaller than such.
Yeah, it's like
Yeah, I guess.
5 or so.
Yeah.
But I think these theories fit within that, is that right?
Those measurements essentially exclude neutron star radius which are too large, right? So equations of state which are stiff. And for those equations of state, so the basic like phenomenology, I think, like for equations of state that predict which are stiffer and predict a larger radius, you would also have an earlier plunge with respect to equations of state that are softer. So maybe if you, but then you'd have to fix some equation of state. I don't know. So the point of view of data analysis, allowing for a generic equation of state and this effect, I don't know if you would have something predicted.
If this was true though, you want to get this scalarization around isolate pulsars, right? So if you have measurements of the equation of state from individual pulsars, you end up finding that the equation of state is different than what you see in binary. That indicate that there's something there.
I don't know if I understood. So
suppose if we can nail the equation of state through isolated pulsars.
yes.
And then if you see a different equation of state from the binary, that will be a fingerprint of scalarization. No? That's what happens.
What about, sorry, after the neutron stars merge, they collapse on the black hole, what happens to the scalar field then?
If they collapse to a black hole, the scalar field gets completely radiated.
Is that very quick? Is that something that you could potentially see in the gravitational waves, or how does that?
Yeah, so the thing is that the direct detection of this like monopolar gravitational wave, so it's not really feasible because the coupling to the gravitational wave and to the gravitational wave detector is proportional to that factor of alpha 0 which I mentioned before. So you have a factor of that small parameter that enters in the detection. Yeah, so I think maybe at least the ways that I have been thinking about were more indirect in the sense of looking at the sort of effects, indirect effects, looking at the quadrupolar visual radiation. So something that I've been working on recently also is like neutron star perturbation theory in this series. So with next generation detectors, we can measure the ring down of the systems. There are some interesting things there. So well, I can discuss this later. It's more specific, but there might be some interesting fingerprints in the ring down phase that can distinguish or help distinguish the field. But here I did not want to focus on like specific constraints to any specific theory, but just to show the general thing of the appearances with non-perturbative effects, which I think it's generally interesting.
Any other questions?
You said studying the ring down like of a neutron star.
like perturbations that do we expect in a version for the remnants to be transparent?
Yeah, you can have low mass neutron stars coalescing. I guess, yeah, there are several simulations that show the basic spectral features of that remnant. And although it's far from what one would compute in perturbation theory, we have, so I'm not going to go into details, but we can chat later if you want. But people know, for instance, that the spectrum of the ring down of this neutron star that's formed in the merger of two has a peak corresponding to the fundamental polypolar modes, which has also some peaks corresponding to quasi-linear combinations of the fundamental polypolar mode and radial oscillations. So these stars are oscillating violently, both in like a quadrupolar way and radially. And there is some non-linear coupling or quasi-linear coupling between this, because the radial modes themselves do not emit gravitational waves, but there is some non-linear quasi-linear coupling that gives some features to the spectrum. And the radio spectrum of these neutron stars is very different. So in particular, so this part, if in the future one can measure this, there would be some interesting maybe fingerprints there. Okay.
So what about this BPN parameter? So I guess you can constrain your parameters that you study for this dynamical scalarization. I mean, the parameters that you obtain should be constrained by the BPN or not?
No, so the BPN parameters.
Which you said is more independent.
Yes, that's just to, yes, so just to first go into an order. So in this theory, the only non-trivial BPN parameters are the first two there, which are related to the classical Eddington parameters. The other, so this gamma and this beta, the rest is all zero in this particular class of theories. And these guys are constrained by solar system observations to be very small. And this translates into, if you remember that at first PN order, these parameters, so that gamma and that beta are more or less like related to this gamma and this beta. It's not the same. You can constrain essentially, so again here, so you expect for weakly gravitating systems like the sun, right? That this scalar charges are proportional to this alpha zero. So measuring this guy from the PPN formalism essentially translates into a constraint on this alpha zero, or if you want of the scalar charge and its first derivative. Yeah. So it constrains in some sense the theory, but constrains very weakly. So this if you think, for instance, of expanding this coupling function of the theory around the background value of the scalar field, the weak field experiments essentially constrain the first term, but not the rest of them. So yeah, so you constrain here. You don't you have a class of theories which has a function in it, so an infinite parameter space. It PPN constraints can be converted into some constraints for alphas.
So more or less, what is this constraint? Or some alpha zero
less than absolute value less than 10 to minus 5, 6.
I see. And this values is something that can be measured, let's say, and can be extracted from measures of the neutron stars.
Yeah, so if you think of parameterizing this really like picking the coupling function and expanding around the asymptotic value of the scalar field, then your solar system constraints will translate into a constraint for alpha zero, but a very weak constraint, for instance, for this beta, which is the derivative of alpha zero, of alpha with respect to the field. And so pulsar timing constrains this parameter much better. And gravitational waves have a similar potential, that they do not, yeah. I can show you some specific constraints if you want. Yeah.
Gravitational